Okay, so gyroscopic precision. It's the reason why a bicycle doesn't fall off and a spinning top doesn't tip over, and it's also the principle how gyroscopes work on many missiles and aircrafts and stuff like that. And it's one of the most confusing topics of physics, of classical mechanics, because it's very unintuitive. What that means is you cannot logically understand this. You can mathematically derive this and explain what's happening, but it's very difficult to understand it intuitively. Today I will be trying to provide an intuitive explanation of this phenomena. So let's start. But first I will give you the mathematical and vector explanation. So many of you might recognize this setup. It's one of the most classical examples of gyroscopic precision. So there's a flywheel attached to an axle, a length of r, and the axle is attached to a rope to the ceiling, and the tension force of the rope is T, and the flywheel is also inducing a force mg. Right in this point, let's assume that the axle has no mass and all of the flywheel's mass is concentrated and only the flywheel's mass is present, and the important thing is the flywheel is spinning this way. If you look from right in this angle, then it's counterclockwise, and this angle is counterclockwise, so the vector of that angular momentum will be right this way. And another important thing is this mg, this induces a torque on this point, and since it's applied downward, the torque is going inside the paper. That's why I use this symbol. And now the vector explanation why this setup precesses is very simple. It's like this, that the angular momentum vector is on this way and the torque is inside the paper, but I have shown you like this. It's like one top view. Now the angular momentum will always try to catch try to chase the torque vector, and that's the reason is Newton's second law. Now as the angular momentum chases the torque vector, since it's attached to this point, the torque vector would also rotate. So this will go on and on and on, and that's the reason why this setup precesses and doesn't fall over. But it's a vector explanation, but it's very unintuitive, because even though I'm explaining why this precesses, we cannot understand why this doesn't fall off, just fall off. Like it's mg is working here, there's a torque, but why doesn't that torque have an effect and tilts this and makes it fall? Why does the angular momentum vector have to chase the torque and not fall off? It can do both, but why doesn't that happen? So there are many explanations online. I've scoured that, but some of them are very good, some of them include many complex orbital mechanics even. So here's a simple one. Okay, so to understand the gyroscopic precision of this setup intuitively, I will be providing you with an analogy, and this analogy has two parts, two cases, case 1 and case 2. In both cases, your goal is to attract this ball toward you and you're at point O. So in this first case, the linear momentum of the ball is 0. So it's very simple, and the ball is attached to a rope, and your goal is to pull that ball toward you. So you induce a force on that ball, and because of this force, the change in the ball's momentum will occur along this line according to Newton's second law, and therefore the ball will slowly come toward you. And this is very simple, it's not very complicated. Now consider case 2. In case 2, the ball is not stationary anymore. It has a momentum toward this way, and you're applying the force toward you on this point this way. So the angle between the momentum and the force is 90 degrees. And by looking at this, you can understand that this ball will go on a circle. But why does it do that? and the reason is, since the force and the momentum, linear momentum of the ball is perpendicular, no change in the magnitude of momentum will occur along the line of the force, or the magnitude of the momentum linear momentum will not change. It will stay the same. But since you're acting a force, since there's a force acting on it, the angle will change, and the angle, let's say, goes from here to here, and the ball travels from point A to point B. Now point A and point B are quite far, but consider them very close. And when the ball goes to point B, the angle the direction of the linear momentum goes from this and to this. Now what will happen to the force? Well, the force is still acting, but since you're bounded to this point, the force is still acting perpendicular to that momentum, and you can see that it's repeated. Like in point A, the force was perpendicular to the momentum. In point B, it is still perpendicular, and this will stay the same for each and every point of this circle. Therefore, this ball goes on a circle and rotates. We all know this, why this happens. Now let's go to the actual example. So now let's consider the main experiment, or the actual experiment, using this analogy. So case 1 for the main experiment is similar to case 1 for this analogy. In here, the angular momentum is 0, or the flywheel is not spinning, but mg is still acting, and therefore torque is still acting, and torque is acting into the paper. The line of the torque is into the paper. Therefore, because of the mg, the setup will just simply fall like this, as you expect. And why does it fall? Because the torque is able to change the momentum of this entire setup toward itself. Like you were able to change the momentum of that ball toward you, the torque is able to change the momentum of this setup toward itself. That's why it falls. Now let's consider the case 2 for this experiment. So here the angular momentum is no longer 0. It's not equal to 0. It is spinning. Therefore, it has the line here. I mean, the angular momentum is acting along this line, and the torque is also here because of the mg, and torque is acting into the paper. So if I draw the torque here, this is the angular momentum, and let's say the torque is here, although it's acting into the paper. Now you can see that like this example, in here also the torque is perpendicular to that angular momentum. Therefore, the magnitude of this angular momentum will not change, but only the direction of the angular momentum will change, like this setup. And suppose this setup rotates at angle of theta. So this is the after a time t, it is rotated theta angle, and now the line of the angular momentum is right here. And now where's the torque? The torque is still acting, but as you can see, this axle is attached to this point. Therefore, the torque will also rotate with theta angle, and the torque will still remain perpendicular to that angular momentum. So in point A, the angular momentum was L. Since it's acting perpendicular, the magnitude will not change, and since it has rotated theta angle, the torque will also rotate in theta angle. So what happened? The condition of case A is the condition of case A is repeated on case B, has repeated itself in B. Therefore, point A and point B are the same, and it will repeat itself point C, point D, and every point of this circular motion that it goes, and that's why it doesn't fall. And because no net change in angular momentum occurs along the line of the torque, exactly like this example where you are pulling that ball towards you, but no change in that ball's momentum occurred along the line of the force. Just the angle changed, and as the angle changed, the angle of the force also remained perpendicular, and it went on a circular motion. and it has repeated itself here. Just the torque force is replaced by torque, and the linear momentum is replaced by the angular momentum. So asking why the wheel doesn't fall off is similar to asking why the ball doesn't come toward you, and that's the reason why when it has a angular momentum, the setup doesn't fall off like in case 1. And thanks for watching. Hope you'll find this helpful.